Alright, as you can see here, I've got this red curve. If this mathy looking curve makes you scared, don't be, it's just a line on a screen. Now we're going to go ahead and add a blue point somewhere on our curve and a purple point somewhere else on our curve. I'm going to go ahead and connect these 2 points with a dashed line, and if you have any sort of algebra background knowledge, you'll know that we can find the slope of this line by finding the change in y between the purple and blue points and dividing it by the change in x between the purple and blue points. Quick side note, we denote change with the Greek letter delta. Now, in looking at this picture, we can see that the slope of our line acts as a sort of rough approximation of the slope of our red curve between the 2 points. And in tandem with this, we see that as we move our 2 points closer and closer together, the slope of our line becomes a more and more accurate approximation of the slope of our red curve between the points. Eventually, we reach a point where our purple point is infinitely close to our blue point. And we find that if we zoom in on our 2 infinitely close points, the section of our red curve between them looks exactly like a perfectly straight line, and the slope of our dashed line perfectly equals the slope of our red curve on this interval. When describing the slope of our red curve at essentially a single point like this, we change our notation and say that the slope is equal to an infinitely small change in y, denoted dy, divided by an infinitely small change in x, denoted dx. Ultimately, this slope of a curve at a single point is what we call a derivative. Derivatives may also go by any of these other names, so be on the lookout for these phrases that really all mean the same thing.